So this is our introduction to Chapter 9, hypothesis tests. This is the second of our two big inference procedures, confidence intervals having been the first one in Chapter 8. The context we're going to use is the Flint water crisis, which some of you remembered when we discussed Woburn in class. If you're not sure of what was going on, you can take a look at some of these captions or do a quick Google search. We're going to work through these notes and I will explain what I have handwritten. I will tell you when to pause the video so you can catch up in actually recording it with yours, but do your best to listen along, knowing that you'll have the time to fill everything in. So the first step being the hypotheses of our state plan do conclude. We have now not just naming the procedure, but we have to identify a null and alternative hypothesis. The null hypothesis is whatever the claim is going to be. So the claim was that the water was in fact safe. There's reason to believe the water was not safe, and so we set out to find evidence against the null hypothesis. In Chapter 9, our null hypothesis, when it's a single sample in 9.2, will be that P is equal to some value, so some claim about the population. When we get to two samples in 9.3, that's the second value or second line of HO, where P1 is equal to P2. So it doesn't matter what the value is, it's just the fact that they're supposed to be equal to one another. And then we'll switch gears to quantitative data for Chapter 11, and we'll end up using mu instead. So all of these symbols are the population parameter because it's what the truth about the population is supposed to be. The trouble is we think something else is going on. So our alternative hypothesis is what we believe before we even collect the data. So if the water is supposed to be safe, we have reason to be suspicious and think the water is not safe. So whatever the value would be, instead of P being equal to, as the null hypothesis states, the alternative hypothesis would be that HA states that P is either less than, greater than, or just different somehow and not equal to the value. Pause the video now and record those notes about null and alternative hypotheses. Our next component, the court system analogy, and I know that I've talked about this in class as well. So we're always working on an assumption. So we assume that a person is innocent. That's the default, that's the null, until we show otherwise, which is that they are in fact guilty. So when we're testing, we either have enough evidence to reject the null hypothesis, or we don't find evidence to reject the null hypothesis. So thinking in a court system, a person is either found guilty or not guilty. They are not found guilty or innocent. So just because we don't have enough evidence to reject doesn't mean all of a sudden we believe that they are in fact innocent. It's just that we didn't have enough evidence to show they're not guilty. So the language we have to pay attention to. You either reject the null hypothesis or we failed to reject it. We will never be accepting the null hypothesis. The logic again behind that is the assumption that the null hypothesis is true with the goal of showing that it's not. So that sort of indirect proof idea, or if you will, the statistical jujitsu in showing that. Our goal in setting out in all of this, we don't believe the null is true. We want to show otherwise. So we are trying to find enough statistical evidence to reject the null, and that evidence then supports our belief, the alternative hypothesis. So without you knowing it, we've been working through these. These are all of those simulations that we've done. Is there convincing evidence of something to support? It is when we looked through a few questions, what's the initial evidence that we have? And it's that if we thought it was a higher rate, then our sample proportion was in fact higher than whatever the claim was going to be. We've also been looking at then with those simulations and with everything in Chapter 7 about sampling distributions and assuming that the claim is true, so that the center is equal to that population center, that we are able to say our sample hardly ever happened. It was very unlikely to happen. And that's what gives us evidence that something else is at play. And that's where we end up rejecting the null hypothesis. How did we see a sample proportion when as master statisticians we did everything we were supposed to? How did we get either so lucky or unlucky that we got something so far away from the truth? Go ahead and pause to catch up. Okay, so logic in terms of the Flint water crisis. Start by assuming the null hypothesis is true. And then we say, if it is in fact true, so that's our assumption, how likely is it that the data we've gathered then is showing that component? So before we just, again, discussed it as probability, we are just rebranding it now as something known as the p-value. So there were a lot of homes getting nasty water in this quote, which makes us think that it is in fact unsafe. So we draw the conclusion under the assumption that it is safe. How did we end up seeing so many homes with bad water? That's pretty unlikely. So we reject that assumption and we're convinced that it is in fact unsafe. So again, the way that we work through each of those is that in our do and conclude steps, we are going to have p-values, just the probability of our sample if the null is true. Alpha levels now, which we've been discussing, just haven't formalized as sort of a cutoff that we'll use, and then the conclusions. So what does it mean to be unlikely? By the EPA guidelines, if more than 10% of homes in a city have unsafe lead levels, so greater than 15 parts per billion, it's considered unsafe. The null hypothesis, you can see, P is supposed to then be equal to 0.1. We're okay if it's equal to 0.1. We're actually okay if it's less than 0.1. It's just, again, scratching the surface in AP stats. We don't identify as less than or equal to. But the alternative, we have problems if it's greater than 0.1. And that's what we think is the case. How did we end up with so many homes that had high unsafe lead levels? Pause and catch up. Okay, so now that you can see both case A or case B, we've talked about the size of sample and what that does in terms of sampling variability. So in something like case A, if we sampled 1,000 homes and 300 of them have high lead, in such a large sample, that's really high if the truth is only supposed to be 10% to end up with something as high as 30%. We would expect with that many samples that that size of sample, that we should be closer to the true value. But in case B, it's only one house. So if it's 2 out of 10, 1 out of 10 would have been 10%. And so because the spread is so much greater with a smaller sample size, it's not so convincing in case B. Go ahead and pause and catch up. So now, what really happened? They sampled 252 homes, so on that higher end of sample sizes, and ended up with 17%. Again, going back to chapter 7, this is just an approximate sampling distribution. But if the truth is supposed to be 10%, then off on the right-hand side there, you can see the mean and standard deviation of the sampling distribution, which means that it is rather unlikely to end up with that p-hat of 0.17. So it's hard to even see. There wasn't much in the tail for me to shade, but that shaded area, which represents the area under the curve, when I find the likelihood that p-hat is 0.17 when the truth is supposed to be 0.1 in these samples of size 252, it's going to be pretty small, and that value is known as my p-value. So anytime you're asked, is there convincing statistical evidence, you are supposed to do the whole 4-step process. So state your hypotheses, work through the conditions. The do step now is like a z-score in finding the probability. We just call them test statistics and p-values. And then we write the conclusion based on whether or not that p-value is underneath the alpha level, if it's less than, or if it's something greater than that cutoff. Pause and catch up. So here is a look at the do step, the test statistic again. In the formula packet, it is there for you. We calculated on the previous page. So again, not a z-score, but now a test statistic. 3.68, still off the charts. As Mrs. Pessy likes to say, it's not even on table A. And so you can use normal CDF if you would like, whichever way, with either z-scores or with the data, and get a crazy small value that's in scientific notation that tells us that there is a very low chance of getting a sample p-hat as high as 0.17 if the truth is supposed to be 0.1. Pause and catch up. So if the p-value is low, as it was, we have convincing evidence to reject the null. Because, again, being masters of statistics, how did we end up seeing a p-hat that is so far from the truth when the null is what they say it is at 10%? If we had not had such a low p-value, then the conclusion on the right-hand side, we didn't find the evidence, so we failed to reject, again, not accepting, just failing to reject. Our p-hat might have just been slightly off due to sampling variability. The significance level alpha is simply a cutoff for what we think is likely versus unlikely, so that we're all using the same sort of goalposts there. So if your p-value is less than your alpha level, we reject the null. If it's greater than the alpha level, we fail to reject it. So the template that is there for the conclusion, I fit in for, or filled in, I should say, for this particular problem. But again, this general formatting, just like we had for a confidence interval, will cover all bases. You'll make your decision, you'll connect it to your alpha level, and then you'll have the p-value in context. Pause and catch up. And finally, the follow-up. So, statistically, working through the little banter there with the mayor, every person on my block still drinks it. It must be just fine. Because again, this is a big deal. And so to be wrong about it, if we end up being wrong, then we end up spending money and resources to fix a problem that's not really a problem. So are we proactive and we're upgrading that infrastructure before we have something tragic happen? It's time and money that if we need to spend time and money on other problems that we know exist, it's sometimes a hard sell to be proactive and work through that. If we found that we were wrong, that we just didn't have enough evidence to say that they were wrong, then we would end up not correcting a problem and the water source would continue as is. And if it's not safe, then all of the issues that come with unsafe lead levels in the population, spending money and resources down the road to care for those individuals. So the last question, a connection to confidence intervals. So if the confidence interval was found, and you can see the little illustration of it off to the right-hand side, this is consistent with our hypothesis test because the conclusion of our hypothesis test was that we were rejecting the null hypothesis. We do, in fact, believe the proportion is higher than 0.1. Not necessarily that it's 0.17. We can end up with a different sample p-hat, but higher than 0.1. Based on our sample size then, the variability, the confidence level that we're using, this confidence interval ranges from 0.121 to 0.213. It is entirely above 0.1. So because 0.1 wasn't even a plausible value for what we believe the true proportion of homes that have unsafe lead levels based on those standards are, we have evidence here again to support what we had with the hypothesis test. The benefit is now that not only do we have evidence that it's higher than 0.1, but we have some estimate as to what we actually think the number could be. So this, again, the foundation of hypothesis testing, working through the logic, trying to make sense of why we do what we do. Hopefully you can see all of the things coming together from the last couple of chapters, because we have been, just with our training wheels on, introduced to all of these things step by step. And so the new part of it really is just the formalizing of it and a little bit with the symbols. This is the end, so you can pause and catch up, and we will move on tomorrow.